Hello students, I welcome you all to my channel Engineers Academy. Do hit the subscribe button if you haven't done it yet. Now we are going to solve this problem which says that the smooth uniform rod AB is supported by a ball and socket joint at A, the wall at B and the cable BC. Determine the components of reaction at A, the tension in the cable and the normal reaction at B if the rod has mass of 20 kg. So we have already I have already solved this problem using the vector approach. Now we are going to solve this problem by using the scalar approach or the scalar method. Since I have told you people in the previous video that I will be solving this problem using the scalar approach, and then you people must compare both the methods. Before going to solve this problem, we need to note down these 2 points, these 2 very important points. So we will use these 2 points throughout the solution of this problem. So what is meant by the scalar method? So by using the scalar method, we will always be finding the moment of a given force or the component of a force by using the F into D formula. So F will be the force or component and D is the perpendicular distance of that force or component from the axis of rotation or from the point of rotation about which we want to find the moment. So now we must read these 2 important points. So the first point is that if a force or component of a force passes through an axis or point about which moment is to be determined, the moment of that force or component about that particular point or axis will be 0. So let's say that if you want to find the moment of a force or component of a force, and if that force or component passes through that particular axis about which we want to find the moment, so that the moment of that force or component will be 0. So we will learn this point, that what is the meaning of this point. And similarly we have another point, that if a force or component of a force is parallel to an axis about which moment is to be determined, the moment of that force or component will be 0. This is very important, since that force or component can only translate the body or system along that particular axis. So we will use these 2 points and we will learn these 2 points throughout the solution of this particular problem. So now we have to consider all the forces on this uniform rod AB. So at A we have the ball and socket joint. So the ball and socket joint can support the reactions in 3 directions. So let's say that we have a X reaction. Here we will have a Y reaction, and in the upward direction we will have a Z support reaction. Similarly at B, this wall can only apply the normal force on this B on this uniform rod at B. So we will have, let's say this will be our BX, since this is parallel to the x-axis, so I'm going to name it as BX. And if we cut this rope, so we will have the tension in this rope. So let me cut this rope first. So if we cut this rope at some particular point, so we will have the tension T here. So we are required to find the tension T in this BC rope, and we are required to find this AX, AY and AZ, and this BX. Let me write that this is that BX, the normal force that is applied by the wall on this uniform rod. And this uniform rod has a mass of 20 kg, so its mass is going to act at the geometric center of this AB rod. So the weight is going to act at its mid length. So let's say that the weight is going to act at somewhere here, let's say, and that will be 20 times 9.81. So 20 times 9.81, this will give us 196.2. So the weight is 196.2 newtons. First of all, we will learn this particular point, this important point. So this important point says that if a force or component of force passes through an axis or point about which moment is to be determined. So let's say that if you want to find the moment about the x-axis, so according to this particular point, this AX, this AY and this AZ, these 3 components are passing through this x-axis, so they are not going to produce the moment about the x-axis. So hence they will not come into our equation if we apply the summation of moment about x equals to 0. So if you want to eliminate these three unknowns, we will be finding the moment about the x-axis, so that will make our life easier. So this point tells us that if a force or component passes through that particular axis about which we want to find the moment, so the moment of those components or force will be 0 about that particular axis. Similarly, the second point tells us that if we want to find the moment of this bx along about this x-axis, so as we can see that this bx, the force applied by the wall on this rod AB, this bx, this is parallel to the x-axis. So if this bx is parallel to the x-axis, so this is not going to produce the moment about the x-axis. So if a force or component is parallel to an axis about which we want to find the moment, then that particular force or component will not be able to produce the moment. If you want to find the moment about the x-axis, so this bx can only translate this rod along the x direction. It cannot produce the moment about the x-axis since it is parallel to the x-axis. So we can imagine that if we apply the force on a door parallel to the hinge of the door or parallel to the axis of the door, so that force will not be able to open the door. So we have that same concept here in this point number 2. So if this bx is parallel to the x-axis, it's not going to produce the moment about the x-axis. Similarly, if you want to find the moment about the y-axis, so this ay is not going to produce the moment about the y-axis since it is parallel to the y-axis. So this is the meaning of this second point. Now we want to find we want to apply the scalar method, we want to apply the scalar approach, and we want to find this t, but we want to have such an equation in which we have this only this t as an unknown. In this particular problem, we have 5 unknowns. We have 1, 2, 3, 4, and 5. We have 5 unknowns, but we are going to select an axis so that we are able to eliminate all these unknowns. We want to eliminate the x, ay, and az and bx, and we want to have such an equation in which we have only this t as an unknown. So using these 2 points, if we find the moment about point A, if we want to find the moment about point A, if we want to apply the summation of moment about point A equals to 0, so then according to this particular point, this ax, ay, and az, they are passing through this point A about which we want to find the moment, so they are not going to produce the moment about this point A, so they will not come into our equation. But this bx is not passing through that point A, so it will come into our equation. And similarly, this t is not passing through that point A, so it will come into our equation. So this will not work, since we want to have an equation in which this t is, so that we have this t as the only one unknown. So now what we can do is that if we apply the summation of moment about the x-axis, that is equals to 0, this will be equals to 0 since this uniform rod AB is in equilibrium. So if we apply this particular condition, then this ax, this ay, and this az, they are intersecting, they are passing through the x-axis, so they will not come into our equation. And along with that, this bx is parallel to the x-axis, so this will not come into our equation. So if we apply the summation of moment about the x-axis equals to 0, so we will have one unknown in this equation, and that one unknown will be this t, which is required. So by selecting such an equation so that we eliminate the remaining unknowns, that will make our life very easier, and then we will be able to find that one particular unknown very easily. So now we are going to apply the summation of moment about x, that will be equals to 0, and this ax, ay, az, and bx, they are not going to produce the moment about the x-axis, so only this t and this w, they are producing the moment about the x-axis. So before going to apply the moment about the x-axis, we need to have the component of this t, since this t is making some angle here. So if you want to find the angle of this t with the horizontal, let's say if you want to find this angle theta, so we have this length, which is 1 meters. So let me write that we have this 1 meter length from this particular point B to this wall. This distance is 1 meters. So using that triangle, we can find, this is that theta, this is 1 meters, and this is 0.5. So we can find this angle theta of this tension T. So that theta will be, if we apply tan theta, so if I apply tan theta, so tan theta will be perpendicular, so perpendicular is 0.5 and the base is 1. So from this we can say that theta will be equal to tan inverse 0.5 divided by 1 is 0.5. So this will give us the angle of that tension in that BC cable, or that BC rope. So tan inverse 0.5, this gives us theta equals to 26.565 degrees. So now we know this angle theta, so we can find the components of this T, and this T will have one component in this direction, and similarly it will have one component in the upward direction. So this component will be, since this component is along the y-axis, so let me write that this is Ty and this is along the z-axis, this is Tz. And let me remove, since we have resolved this T, so I will remove this T now. So now we have two components of that tension in this BC rope, so Ty and Tz. So we can find Ty and Tz. So this is along this particular line. Along this particular line we have T, and this is we have that Ty, and this is our Tz. So now using that triangle we can say that Ty will be the T cos of theta, since the angle is made with Ty component, so T is not known, and cos of theta is 26.565. So cos of 26.565, this is 0.8. We can say that this is 0.894T. This is Ty. And similarly, Tz is the sine component of T. So that will be T sine of theta. And sine of, this is T sine of theta is 26.565. So sine of 26.565, this gives us 0.447T. So this is Tz. So now we have Ty in terms of T and Tz in terms of T. So now we are going to apply the summation of moment about the x-axis equals to 0, and by applying this condition we will have only one unknown in our equation, and that one unknown will be that tension T in the rope. So now if we apply the summation of moment about the x-axis, so as I have discussed that this Bx is parallel to the x-axis, it's not going to produce the moment about the x-axis, and these three components, they are not going to produce the moment about the x-axis. So this Ty and this Tz, they are going to produce the moment about the x-axis. So now as we can see that this Ty will try to produce the moment about the x-axis in this direction. So it will produce the moment in this direction. So if we curl our right hand fingers in this direction, so the thumb will point out in the positive x direction. So this Ty is going to produce the positive moment, that is in the positive x direction, that is in the positive I direction. So this is going to produce the counterclockwise moment about the x-axis. So the moment produced by this component will be Ty multiplied by the perpendicular distance. We will be going to use this particular equation, since this is the scalar equation for finding the moment. So Ty multiplied by its perpendicular distance from the x-axis. So the perpendicular distance of this Ty from the x-axis is 2 meters. This is the perpendicular distance of this particular component Ty. So we will write that this Ty is producing the counterclockwise moment, since the thumb is pointing out in the positive x direction. So we will write Ty, and the perpendicular distance of this Ty from that x-axis is this distance, which is 2 meters. So I will multiply this with 2. So we have plus 2ty. Similarly, this tz is going to produce the moment about the x-axis in this direction, like this. And if we curl our right hand fingers in this direction, so the thumb will point out in the positive x direction. So again, this tz is also producing the counterclockwise moment about the x-axis. So again, we will write plus tz, and the perpendicular distance of this tz from the x-axis is this distance, or we can say that this distance, and this distance is 1 meters. So tz into 1 will give us the moment of this component about the x-axis. So this is multiplied by 1. Similarly, this weight is going to produce the moment about the x-axis in this direction. It will try to rotate, it will try to produce the moment about the x-axis in this direction. And if we curl our right hand fingers in this direction, so our thumb will point out in the negative x direction. So this weight is going to produce the clockwise moment about the x-axis. So we need to write the minus sign, and the weight has a magnitude of 196.2, and the perpendicular distance of this weight from that x-axis is the half of this 1 meter, since this weight is acting at the mid length of this bar. So if we project the axis, the line of action of this weight, so it will intersect with the ground, and that intersection point will be at a distance of 0.5 meters from the x-axis. Since this weight acts at the mid length, so its projection will be at a distance of half of this length and at a distance of half of this length. So this means that the perpendicular distance of this weight from that x-axis is 0.5. So this is the moment arm of this weight from the x-axis. So we will multiply this with 0.5 meters, and this is equal to 0. So now, by applying this equilibrium condition, that is the summation of moment about the x-axis, we have eliminated the 4 unknowns. We have eliminated ax, ay, az, and this bx, and we have this equation which have only one unknown. Since ty is, we have ty in terms of t and we have tz in terms of t. So by substituting ty and tz, we will have only one unknown in this particular equation. So now let's substitute that ty and tz in this equation. So we will have plus, and ty is 0.894t and tz is 0.447 minus, this is 0.447 into t. And if I bring this term to the other side of equation, it will become positive. So we will have, this will be equal to plus 196.2 into 0.5. So now from these two terms, we can take the t common. So we can write that this is t, and 2 into 0.894 plus 0.447. This is equal to 196.2 into 0.5. So now we can sum up both of these. So this is 2 into 0.894 plus 0.447. So this is 2.235. T equals to 196.2 into 0.5. So from this we can say that T is equal to 196.2 into 0.5 divided by 2.235. So 196.2 multiplied by 0.5 divided by 2.235. So this gives us T equal to 43.892 newtons. So by using these two important points, we have eliminated all those unknowns, and we got the value of T using this only single condition of equilibrium. So using these 2 points very smartly, we can eliminate the remaining unknowns, and that always makes our life easier while solving this kind of problems, while having the equilibrium of a rigid bodies in 3D. Now once we have this t, we can put that t value in this ty and tz. We can find the magnitude of ty and tz. So now the magnitude of ty will be 0.894 into that t, which is 43.892, and similarly we will have 0.447 into 43.892. so let me find ty. So ty is 0.894 into 43.892. this gives me ty. Let me write that ty equals to, let me write it here, this ty is equal to 39.239 Newton, and similarly tz is equal to, so tz is 0.447 into 43.892. this will give me 19.620, let's say 19.620 Newton approximately. So now we know the components of t, z and ty, and we know the magnitude of that t as well. So now if we apply the summation of forces along the x-axis, the summation of forces along x-axis, that must be equals to 0, since that's uniform bar is in equilibrium. So we have to add up all the components along the x-axis. So we have this ax, this is acting in the negative x, so I will write minus ax, and we have this bx, this is along the positive x-axis, so we will write plus bx, and this will be equals to 0. And from this we can say that minus ax is equal to minus bx. So if we divide both sides by minus sign, so ax is equal to bx, ax is equal to bx, but we do not know the value of ax, so ax is equal to bx, but we have to find the value. Similarly, if we apply the summation of forces along the y-axis, that must be equals to 0. So now we have to add up all the components along the y-axis. So we have this ay and we have this ty. So ay is acting in the positive y direction and ty is acting in the negative y direction. So I will write plus ay minus ty. So this is the magnitude of ty, which is 39.239. So this is 39.239. this is equal to 0. This is basically ty. So ay is equal to ty is equal to 39.239 Newton. So this is ay. Similarly, if we apply the summation of forces along the z-axis, that must be equals to 0. So we have to add up all the z components. So we have this az, this is acting in the positive z direction, so plus az. Then we have this tz, this is acting in the positive z direction, and tz is 19.620, so plus 19.620, and the weight is acting in the downward direction, so that is minus 196.2. this is equal to 0, and from this we can say that az is equal to 196.2 minus 19.620. so az is equal to 196.2 minus 19.620. this gives me 176.580 Newton. This is az. So now we know ay, we know az, we know that t. So we have to find either ax or bx, since ax is equal to bx. So now we have applied all the summation of forces along x, y and z. So now we have to find out such an equation in which we will find either ax or bx. Now if we apply the summation of moment about the z-axis, so if we apply the summation of moment about the z-axis, so as we can see that this az is parallel to the z-axis, it's not going to produce the moment about the z-axis, and this ax is passing through that z-axis, it's not going to produce the moment about the z-axis. So, and this ty is passing through the z-axis, it's not going to produce the moment about the z-axis, and this tz is parallel to the z-axis, it's not going to produce the moment about the z-axis. Similarly, this weight is parallel to the z-axis, so it's not going to produce the moment about the z-axis. So this will make our life very easier. This ay and this bx, they are only producing the moment about the z-axis. So let's mark all these. This tz is parallel to the z-axis, it's not going to produce the moment about the z-axis. This ty is passing through the z-axis, it's not going to produce the moment about the z-axis. Similarly, this az is parallel to the z-axis, it's not going to produce the moment about the z-axis. This ax is passing through that z-axis, it's not going to produce the moment about the z-axis. Similarly, this weight is parallel to the z-axis, not going to produce the moment about the z-axis. And only this bx and this ay, they are going to produce the moment about the z-axis, and we know the magnitude of ay, which is 39.239. so by applying the summation of the moment about the y-axis, that will solve our problem. That will give us bx, since we will have only this bx as an unknown if we apply this condition. So the summation of moment about y-axis will give us the magnitude of this bx unknown. So now this bx is going to produce the moment about the z-axis in this direction. So it will produce the moment about the z-axis in this direction, and if we curl our right hand fingers in this direction, so the thumb will point out in the negative z direction. So this bx is producing the moment about the z-axis in the clockwise direction. So that is why we have minus sign. So I will write minus bx, and the perpendicular distance of this bx from that z-axis is this distance, which is 1 meters. So the moment arm of bx from the z-axis is 1 meter. So we will multiply this with 1. Similarly, this ay is going to produce the moment about the z-axis in this direction. And if this is going to produce the moment about the z-axis in this direction, and if we curl our right hand fingers in this direction, so the thumb will point out in the positive z direction. So this means that this ay is producing the counterclockwise moment about the z-axis. So we will have plus sign ay, and the perpendicular distance of this ay from that z-axis is this distance, which is 1.5. so we will multiply this with 1.5. so this is ay into 1.5, this will be equal to 0. So now from this we can say that minus bx is equal to minus 1.5 ay, and from this we can say that bx is equal to, minus sign will cancel out and we will have 1.5 times ay, and bx is equal to 1.5, and ay magnitude is known, which is equal to ty, and that is 39.239. so 39.239, this is equal to, so now from this 1.5 multiplied by 39.239, this gives us 58.859, let's say 58.859 Newton. This is bx, and from this equation we know that ax is equal to bx. So I will write that ax is equal to bx is equal to 58.859 newtons. So the tension in that rope is 43.892. ax is equal to bx is equal to 58.859 newton, ay is equal to 39.239 newton, and az is equal to 176.580 newton. So this is the solution of this particular problem using the scalar method. Using this equation, the moment is equal to force times the perpendicular distance. Whenever you people are going to solve such kind of problems, always consider these 2 points. They are very helpful, and search for that particular axis or point which will eliminate most of the unknowns. So that will make our life very easier while solving such kind of problems. I hope this will help you in your learning. Do let me know in the comments if all these problem solutions helps in your learning. Do subscribe Engineers Academy for the solution of such more problems from Hibbeler statics.